Can we please start talking about neurons? The word we want to hit with nerve cells is ganglia. Ganglia is a group of neurons. Now, I don't know how you grew up in a neighborhood, but in my neighborhood, I learned quick. If we're going to jump someone as a child, that's what we used to do. We just used to commit felonies. If you're going to go jump someone, it's better to have a gang. Therefore, if you're going to process a neural signal, you want your nerves to fire in a gang. One neuron by itself, not that impressive. You wrap a whole bunch together and call it a ganglia, you can process a lot of information very quickly and very efficiently. Make an animal noise when you're done. Okay.
What animal was that?
None of you are going to make a fox sound. You're not ready. All right, can we move on? Let's talk about how a neuron fires. Let's talk about how a neuron fires. But we're going to do it. We did that yesterday, so we're going to talk about this. Got a lot of vocab to go over, and I'm going to repeat this over and over and over again in the process and explain it slightly different using different vocab each time. But as we know, repetition is the mother of learning. Neurologically, the more you do something, the stronger the connections between. How a nerve fires. Step one. Dendrites receive a chemical called a neurotransmitter. And one way to imagine a neurotransmitter, and a metaphor, is that it's a key. Does the key unlock the next cell's dendrites? And we've got a lot of different types of neurotransmitters. We're going to get into them. Some are responsible for sleep. Some are responsible for mood. Some are responsible for not letting a neuron fire. Why would you ever want a neuron to not fire? Think about sleep. You don't want your motor neurons to fire when you're dreaming. So we're going to get into neurotransmitters a little bit later, but please know, just as complex as the fact that we have a whole bunch of neurons talking to a bunch of neurons, they use different words, and the words are, of course, neurotransmitters. So they talk to each other, they don't use words, they use neurotransmitters. That goes to a receptor site. A receptor site is a hollow tube on the dendrite, and if you want to think of the word a receptor site, I want you to think of the word a lock. The right key has to go in the right lock. When you're done writing that, one more time, make an animal sound. Nice. I like it. Okay, that triggers the axon to let in positively charged sodium ions. Go ahead. A dendrite? The quickest way to remember what a dendrite is just use the word an antenna. Or you can imagine the leaves of the tree. The leaves of the tree receive a chemical signal, or a solar signal called sun. And I guess a chemical signal of carbon dioxide. And that might signal the tree to do something. So you can imagine a dendrite's an antenna. It receives a signal. When the dendrites receive enough and the right kind of signal, we're going to learn about something called threshold. When threshold's reached, when the right key opens up the right lock, then we're going to let in sodium ions. Basically, your neuron, your axon's a big battery, or actually a really, really small battery. The reaction between the positive ions and the negatively charged axon create an electrical charge. The fancy name for the electrical charge is called an action potential. When you have an exchange of charged particles, it's going to create electricity. That electricity is going to run down the axon at variable speeds. Of course, it's going to be really fast, but you're going to have different speeds for different signals and different axons. There's different variables as to why different types of axons are going to be faster than other types of axons. Look at the variability of speeds from 9 feet per second to 400 feet per second. And one of the major variables, you don't have to write the word down now, but one of the major variables to how fast a neuron travels is going to be how well the axon is insulated. If the signal going down the axon is in a non-insulated axon, it's going to be slower. If the axon is insulated with a fatty tissue called myelin, myelin is, for lack of a better word, insulation. It's fatty insulation on an axon. But let's go back. We don't want to hit myelin quite yet because we've got to talk about glial cells a little bit more. As the electricity, the action potential, or the charge, screams down the axon at speeds that are, well, amazingly fast, it's going to come to a screeching halt. And it's going to hit what's called the end bulbs. Now, there's another way to call it end bulbs. We could call it axon terminals. One of the problems with this chapter, with this unit, is the fact that we've got a concept, and maybe you're starting to get the concept, but there's so much vocabulary floating out there. And sometimes there's 2 and 3 and 4 terms for one concept. So for our purposes, we're going to say end bulb is the same thing as an axon terminal. And when you hear the word axon terminal, just think of end. A term paper happens at the end. A terminal disease, well, you know what that's the end of. All right, an airport terminal is the end of your journey. So axon terminal is the end of a neuron. We know that electricity goes there, it stops. Why? Because it's not going to jump the gap. There's not enough electricity. So what's going to happen there? It's going to release another chemical. That chemical is going to burst out, cross the gap, and talk to not one neuron, but a whole bunch of other neurons by unlocking the receptor sites on the dendrite. What's up? You're just sitting like that? That looks extremely uncomfortable. Okay, fair enough. Everyone try it. You won't try it. Everyone put your hand right over here and just rest it. Okay. Which again brings me back to my invention of a hat pillow. Wait till I invent 3-bladed scissors. You know what I'm saying? Now we'll be cutting something. Okay, we're talking about a neurotransmitter, and I said, look, man, we've got a lot of words to describe the same thing. The chemical jumps of space called either the synapse, synaptic gap, synaptic cleft, synaptic chasm. And this is confusing because we haven't gotten to the memory unit yet. But when we talk about, well, where are memories stored? They're not stored in a certain brain structure. They're stored all over the brain. Where are they stored? They're not in a neuron because a neuron's filled with charged ions. Where would they be stored? We're going to find out that memory is actually stored in the synapse. Now that's going to confuse you because you say, how could something be stored in a space? There's nothing in the space because if there was something in the space, it wouldn't be a space. You don't believe me? How much dirt is in a 1 cubic foot hole? 1 foot deep, 1 foot wide, 1 foot across. There's no dirt because it wouldn't be a hole if there was dirt in there. So if there can't be anything in the synapse because then it wouldn't be a space. But then how can memories be stored in a space where there's nothing in there? One more time, tell me when you're done writing by signifying with an animal noise. Sniffling does not count. Not bad, that was pretty good. We're playing for Hershey Kisses.
Ooh.
And now it's for real. Now I want to hear some real animal sounds. Now you got to feel it. You can't just say meow. You got to feel it. You got to channel your inner sheep. Or nicely done. Nicely done. You get a sticker. Pass that back. Well done. All right, so check it out. The whole process starts again with another neural cell. Let's talk about something called the all or nothing response. I call it a digital phenomenon. Either a neuron fires or it doesn't. All right, my computer dorks are going to know that we're going to call this binary. What the heck are you talking about binary? Either a signal is sent down the axon, electricity is created with an action potential, or it's not. Now, what's the signal for this? Who's going to decide whether it fires or not? And the word, one more time, you heard me mention before, it's called threshold. If for lack of a better word, the lock is unlocked by the key. If enough and the right kind of neurotransmitter hit the dendrites, then we're going to fire. And how fast are we going to fire? As hard as we can. There's no in between. Some people are like, well, is that when I have a tip of the tongue phenomenon? I mean, I'm thinking it, but I can't quite remember what it was. Maybe my neurons didn't fire as hard as they can. No, it doesn't work that way. Okay? But if you were to squeeze the trigger, it doesn't matter how lightly you squeeze the trigger. It doesn't matter if you really squeeze. The bullet's going to leave the chamber at the same speed no matter what. The action potential is going to fly down the axon at the same speed no matter what. So that's called the all or none law. Okay? And it's respondent to something called threshold. Is enough chemical and the right kind of chemical stimulating or tickling the dendrites? Questions on this? All right, one more. Resting state / resting potential. This is what happens when the neurons are not firing. They're waiting for their dendrites to be tickled. They're waiting for threshold to be reached. They're not firing. They have the potential to fire, but right now they're at rest. What does this mean? This means that the neuron is, and we're going to learn this word when we talk about recharging the neuron, it means the neuron's polarized. Polarized means separated. It means our Congress is polarized. One side over here, one side over here, Democrats and Republicans. So your resting state is when the charged particles are separated. And after you're done with this, we're going to go and take a look at a drawing and see if we can compare a neuron to a battery. I don't hear any animal sounds. Some of you are shy. That was pretty impressive. I felt, all right, the quack was okay. It was a little foul. Get it? All right then. But what we're looking at, you got... All right, now we're getting there. Some of you are so worried when everyone else thinks. Look around this class. Ain't nothing but ugly children. Why would you care what they think? All right, let's start drawing. It's so mean. Someone in the back, like, it's true, my mom was right. All right, so here's what we're looking at. All right, let's draw ourselves. Let's draw ourselves. Here's the cell body, otherwise known as a soma. Here's the nucleus. You got a whole bunch of other organelles floating inside the cell. Of course, we're going to have the antennas. How long are dendrites? Well, of course, that depends on the type of the cell and the function you're asking it to do. And you're going to have the long, hollow tube we're going to call the axon. All right, and then you're going to have these things called axon terminals, or some people call them end bulbs. And they kind of look like a bulb. They got a swollen thing at the end. So what I want to talk about is the process by which you have sodium ions, which are positively charged. They really want to get inside the axon. I'm going to use the analogy, it's fall time. And if anyone's noticed, there's a lot more deer. The deer have declared their annual war on car fenders. The deer are like, well, there's a car, let's go get it. How many of y'all have ever been hit by a deer? Like, now you haven't hit the deer's like, there's a car, let me go crush it. But, so the male deer in the fall, they get a certain feeling, if you will. And they really want to get with the female. So we're going to call the analogy of the sodium molecule, the male deer, man, it wants to get inside the axon like really badly. So much so it's like willing to hurdle cars for it. Now, the female deer inside the axon are like, I don't know. All right. I can't believe I just did that. So, under what condition, something's seriously wrong with me, my therapist is not doing her job. So, under what condition, under what criteria are we going to let the sodium in there? Well, it has to reach threshold. What do we mean? You have to have the right kind of neurotransmitters and the right amount tickle the dendrites. If they unlock the dendrites, we're going to let the sodium in. How are we going to let the sodium in? It's going to be something called a sodium gate. Sodium is let in kind of segment by segment. First, it's let in at the axon nearest the soma or cell body. Then when that gate opens, then this gate will open, then this gate will open. And what's going to happen is we're creating an electrical charge and it's going down the axon. Questions so far on that? As the electrical charge goes down the axon, it's going to go hit the axon terminal. We know the electrical charge is not going to magically jump because then you'd have a spark in your body. And the only real good way to have a spark in your body is what? Wintergreen Lifesavers. Who knows what I'm talking about? If you got homework then, I'm a little disappointed in your parents. Go get some Wintergreen Lifesavers. All right, and then put them in your mouth, go in the bathroom, turn the lights off, and you'll see sparks in your mouth. Yes, lightsabers like a Jedi. You have just erased the goodness you've done from your animal noise. You're now at -1 again. All right then, so one more time. This is kind of cool. This is kind of cool because we can really understand that, well, I'll tell you what. Does anyone here have a Gatorade bottle? You got a Gatorade bottle with you? All right, can you please take the Gatorade bottle out, and can you please read us the ingredients?
Water, sugar, dextrose, citric acid, natural flavor, salt, sodium.
Salt, sodium. And I bet if you keep reading, you're going to come across the word potassium. Monopotassium. So what the heck does this mean? Theoretically, The story behind Gatorade is the Florida Gators football team in the 60s. They're doing 2-a-days, and they're doing it in Florida in August, hot, humid, and these are very healthy young men. They're drinking a lot of water. They're still passing out. They're still cramping up. And the coach is like, you drinking water? They're saying, yeah, coach, I'm drinking water. And you realize, if you've ever had sweat in your eye, if you've ever had sweat in your mouth, it stings. It's salty. Because when you sweat out, you're not just sweating out water, you're sweating out salt. And one of the theories that is out there is that for endurance athletes or people who are sweating so much, drinking water is not enough because you're sweating out more than just water. So theoretically, Gatorade is designed to replace the important salts, electrolytes, and ions that your neuron needs to fire, sodium and potassium. Long time ago, in the Songhai Empire in the 1300s, when they traveled across the Sahara Desert, they'd have to bring salt with them. So they drink plenty of water, but they'd also eat a handful of salt. Now, in our diet, you don't ever have to worry about salt. I double dog dare you, unless you're like a straight up vegan, all right? You don't ever have to worry about salt in the average American diet because there's salt everywhere. It goes to show you that salt is that important, and rarely does it happen that you can die from too much water. Is it too much water? No. It's the fact you don't have enough salt to run your neurons. Okay, so what does this really mean? What if I could show you how important salt is to the neural firing? Do you think that if we could we create like a squid zombie? Like, what are you talking about? Purposely, again, I think zombies are out there. I think they're coming. We don't know this yet. And it bothers me. There are, again, some families that raise their children to be nonviolent. What's going to happen when the zombie happens? So, I know, that's right. Why would he even say that? So let's take a squid. Let's cut its head off and stimulate its neurons. Do you think the squid will move? Let's take a frog and we cut out its head or cut off its head and we zap its muscle with electricity. Will it twitch? Yeah. Could you do it with a human? What if you were some sick Professor Doofenshmirtz like mad scientist, right? And you have someone on a lab table and they're freshly dead and you start zapping the brain. Could you get the arm to move? I think so. Could you get the leg to move? I think so. Could you get them to think? Feel an emotion? That's a wild thing. I think the seeds have been planted for such things. Should we pursue it? Do we want zombies? Or it would make taking out the recycling a little bit more interesting. Obviously, I know, right? Cover me, I'm going. All right, so obviously I'm being a little bit facetious, but let's watch the squid. Let's watch the squid zombie video, and you can kind of see for yourself the importance of sodium, okay, on neural functioning, even on an animal that's dead. When we look at the squid video, I said things like, is it trying to escape? No, I don't think there's any intentionality. And actually, this is a predictor of what we're going to talk about when we get to the consciousness unit. Okay? Not only are we alive, we know we're alive. I don't think simple creatures know they exist. They just simply react. Okay? And we're going to talk about, believe it or not, what is a zombie? Does it have consciousness or is it just a reaction? So when we look at that squid flailing around, is it random? Is there any thought there? And we'd have to really ascribe. I heard someone like, oh, because you saw the dead squid trying to, that ascribes intentionality, it means that thing has a purpose. Escape. Escape what? It's already dead. And so this is an interesting concept when we think about what is thought, but that's kind of a predictor when we get to the unit on consciousness. You know all those really annoying coaches and like music teachers that say you got to practice, practice, and every now and then there's a teacher who says you cannot wait to the last minute. You cannot cram. Cramming doesn't work. They're right. They're actually right on a neurological level. And the term we got to know is called long-term potentiation. It simply means the more often a neuron talks to another neuron, the better friends they are. The better friends they are, the better they can communicate. The better they can communicate, the better friends they are. You and your friends, I would imagine there are some people, and I've seen it in my class, they'll look across the classroom and they'll like nod at each other, and the other friends are like, mm-hmm. And like I think a whole conversation of information just went through that one nod. That only happens, information flow only usually happens among good friends. So what does this mean neurologically? It means if neuron A reaches out and talks to neuron B, and they exchange, not words of course, they exchange chemicals, whether it's dopamine or serotonin or GABA. These are words we're going to know in a little bit. If they only do it once, maybe they're going to forget. Maybe they won't ever talk again. How does this relate to right now? We're using psychology to teach psychology. So far in this lecture today, we have actually talked about some words, and some of you sort of get it. We've got a couple words under your belt. If you do not go home and practice, I'm not sure about the strength of that synaptic connection. But if you go home and read your book, and like, oh yeah, this is what, and I get it, and now what you're happening is the more you ask those neurons to talk to each other, the more they're going to talk to each other. It's a fancy word for saying practice. It's a neurological word for saying practice. So long-term potentiation, you wrote down a long, fancy definition. All you got to write down is learning through practice. And this is athletics, this is academics, this is music, this is remembering someone's name. Anytime you want to learn something, you got to practice it. Here's a fancy little saying. It even rhymes. So what I want you to do, I want you to write it in cursive. Switch up. Like, ooh, some of you are pretty fun. Calligraphy, if you will. Neurons that fire together, wire together. Neurons that fire together, wire together. So people who have developed a pretty strong skill musically, people who have generated a strong skill or developed a strong skill athletically, it's because they've practiced. Talent, of course, makes a difference. But is talent neurologically the fact you're born with more connections? Maybe. But the way to get more connections is to practice. So now we look at this. This is actually a blend between the behavioral paradigm, kind of the behavioral approach to psychology, and the neurological. Remember, Skinner said, all things are because of reward and punishment. All things reward and punishment. He taught a rat that the reason the rat's going to do something is going to get a reward. Now, this is an interesting concept because we're going to talk about habits and bad habits. Skinner said the reason you have a habit, a bad habit even, is because on some level, you get a reward for it. And the more you do it, the more rewards you get. Okay, this is true, but now we're going to explain it biologically. The more you do a behavior, the stronger the neural connection. The stronger the neural connection, the more you're going to do behavior. So who's right, the biologists or the behavioralists? And the answer is yes. It doesn't have to be an either or, Hatfields, McCoy, Cripps versus Blood war. It used to be like that, believe it or not. Psychology used to have some pretty segmented divide. Here's the word for it, because we're going to learn as we talk more about neurons. Psychology used to be polarized. Nope, it's behavior. Nope, it's chemicals. And we're finding out basically they complement each other. Do chemicals cause behavior? Yes. Does behavior cause chemicals? Yes. Let's take a look. I'll even turn the lights off for you guys. How much time we got? Okay, fair enough. We're going to watch another video. We might even watch the video again. All right, so what are we looking at? The brain, neural tissue. And I think you can see, I can't even imagine how small this would be. I don't know if it's 1 millimeter, 1/2 of a millimeter, 1/10 of a millimeter, 1/millionth of a millimeter. What we're basically suggesting is you can see the soma, which is of course the cell body. Okay, you can see long spiny axons branching out. It's kind of tough to see dendrites. We see a jumble of faint lines, dendrites and axon terminals. Of course, we can't see the fact they're not touching. They look like they're touching. But remember, if we were to use the analogy, I double dog dare you to look back behind your computer. Look behind your TV. You got a whole bunch of wires, and they look like they're touching, but only the insulation is touching. You don't believe me? I would like you to go home shave off all the insulation off of the wires behind your TV, and then allow them to touch, and let's see what happens. All right, I think it'd be kind of interesting for short term only. Is that lack of myelination a source of neurological disorder? I think so. All right, so we got that. Is it video time?
Yeah.
Nice. Has there ever been a situation where a teacher asks, is it video time? And students are like, no. Has that ever happened? I don't think so. Good. All right, we're done. All right. Whatever. Okay. All right, your feelings are irrelevant. Know that. Everyone got a pen? What's government shutdown? It's when all the ninjas refuse to come into work.